with the flip side of that story. It's about the bacteria that we don't want inside of us. One thing, 100 years ago, about half the people in this room would have died of some kind of bacterial infection. But with the medicine that we have now, it's about one person out of all of us. So, first off, what is an antibiotic? Well, an antibiotic is any kind of drug that fights a bacterial infection. And over the years, since 1940, we've developed a lot of them. All of the different names on here are different antibiotics. And you can see that it started off in the 1940s, and then around the 60s and 70s, the golden era of pharma, we were discovering tons of different antibiotics. It seemed like we were going to have an infinite supply of them, that no matter how many we burned through, we'd be fine. But then around the 80s and 90s, that sharply declined. And now we're hardly approving any new antibiotics, partially because they're getting harder to find, and because drug companies just don't have the incentive to make them when we already have all of these. Any new antibiotic they make will be used as a last line of defense. But it's really important that we do make new antibiotics. So right here are all of the major classes of antibiotics. Now, I want you guys to look at this, and how many of them up there do you think have no resistance whatsoever? Just guess. Well, it turns out that we have never designed a drug that is completely immune to resistance, and we're never going to. Every single antibiotic that we create will at some point have immunity developed to it. Now, that's because these drugs, they obviously can't harm us, so there's a way that life can get around it. And because bacteria are so vast, they're everywhere, there are so many of them, there's always going to be one of them that finds a way. Now, the great thing is there's never been a type of bacteria that's developed a widespread resistance to every single one of these. So we've always had a last resort, but we have to be careful. We have to not waste these, not use them for everything, to make sure that there isn't something that looks like this. Now, how does antibiotic resistance happen? I'm throwing that out there a lot. So we get sick and there's a bunch of germs in our gut, but then, we take some antibiotics, it knocks out almost all of them, but we make a mistake. We think, oh, I'm feeling better, so I'm just gonna stop taking these. And it turns out there were a few of those germs in our gut that were just a little bit better at resisting this antibiotic than the others. And because we didn't take it for the full amount of time, those ones have been able to survive. And now that we're off that antibiotic, they're repopulating, and now there are millions and millions of them. And even though before they were only a little bit better, of those millions or even billions, one of them has had another mutation, and now it's a lot better. Now it's completely resistant. And bacteria have ways of taking that information and transferring it to other species. They can transfer it either through these pili that they send out, or they have these plasmids, little circular bits of DNA that can go from one to another, and there are all kinds of ways that they can develop this resistance. They can say, pump the drug out so that they don't even have to deal with it. They can have some enzyme modify it so that it's no longer effective. Or they can have a mutation at the target of whatever this is. And just a single point mutation, just one change in a DNA base can make a bacteria completely resistant to an antibiotic. So here's a little picture that looks a little bit like what Tyler showed you, showing that these prokaryotes, these bacteria, they're a lot simpler. There's a lot less going on than in our cells. And that's a good thing that we're different. The more differences we have, the more different types of antibiotics we can create. We want to take advantage of those differences. So this is just a chart. I'll go through it point by point. Bacteria have different cell membranes, and they also have cell walls. We just have cell membranes, so if we can find some kind of drug, like penicillin, we've all heard of that, the first antibiotic discovered, attacked the cell walls, because that's not going to hurt us. We don't have to worry about that. Or we can have something that takes any kind of pathway. So folate, for example, We get that from our diets. But bacteria, they have to make it for themselves. So if we can target some protein in that folate synthase pathway, we can then harm them without doing any damage to ourselves. Another one, Gyrase Rna Polymerase, those are part of the replication process. And bacteria replicate different now. You've also probably heard, a lot of you in your biology classes, that our mitochondria are a lot like that. Their replication process is a lot like that of bacteria. So we have to be a little bit careful with these. That's why you're seeing fewer classes in these, because there are a lot more similarities and we're a lot more likely to harm ourselves. Now, the 30S and the 50S subunit of ribosomes, a lot of you have taken biology have probably also heard that's different. Humans, we have a 40S and a 60S subunit. So if we can attack that, we can create all kinds of different antibiotics. Now, where are we going to come up with these ideas? You know, we know what we want to target, but we're not just going to think up some molecule. So penicillin, the first antibiotic, was found in mold. And we can take things like that, just a gross looking orange, and turn that into medicine. And we can look all kinds of other places. We can look in the foods we eat. And now, since we've gone through a lot of the easy places, we need to find more extreme environments. So we want to look at coral reefs like you see here. We want to look at hot springs and in rainforests. And there are people here at Yale who are doing stuff like that. So if you guys go into science, there's a huge field of natural products where people go to crazy places trying to find these. There's an undergraduate class here that goes off to the rainforest and collects fungal samples, trying to find these sort of things. And what we do end up finding are complex molecules like this. This is erythromycin, which is found in soil bacteria. And if you just look at it, can you imagine trying to just design something like that? I mean, I never could. But luckily, nature's already done that for us. And then we can take this molecule and we can change it. So if you try to spot, this up here is erythromycin, and then this is roxithromycin and clarithromycin. If you can see the differences, try to spot them. What we can do is we get great chemists who are like, okay, we have this, how can we change it a little? They'll look at the protein, they'll look at where it's binding, where they can make it fit just a little bit better. And sometimes a bacteria can become immune to this one, but it's still susceptible to these two. So we want to try to create as many different variations as we can. So did you spot those two differences? And another really cool thing that we can do is bacteriophage therapy. So it turns out that bacteria have a natural enemy called phages. They're viruses that just infect bacteria. They don't infect our cells at all. They're completely safe for us to take, and they're actually already in us. Now, you're probably thinking, if this is around, why haven't we tried it before? But we actually did. Before antibiotics were developed, this was a common treatment. And the Soviet Union actually used it up through the Second World War because they didn't have more advanced technology. And the cool thing about this is each bacteriophage is specific to one species of bacteria. So if you know that someone has MRSA, you can knock that out without actually doing damage to their microbiome, which, as we just learned, is very important. So all of these are great ideas, and if you're wondering, what kind of work can you do? All kinds of stuff. You can work with microbiology directly with these bacteria. You can work in a clinical setting if you want to work in a hospital testing people who have antibiotic-resistant bacteria. You can do the kind of stuff I do with biochemistry and molecular biology. It's a picture of me plating some cells. You can work as an organic chemist, synthesizing these molecules, figuring out what the best way to do that is. And even more recently, looking into computational chemistry, so taking these targets and trying to design programs that will come up with molecules that we can then give to the organic chemists to make and test out. So I haven't actually talked to you about the research that I do because it's a little more technical. But if you are interested in learning more about that, feel free to talk to me afterwards. I would love to tell you all about ribozymes, which is what I do. So does anyone have any questions? Okay.